Welcome back, class. So today we are going to talk about heat and work, and we're going to start off by looking at how we quantify heat. So we have a specific equation that we use, and if we look at it, generally we have Q, and Q is heat. We have C, which is what's called the heat capacity, and we have delta T, which is our change in temperature. So just in general, let's think about anytime we want to think about change in temperature, remember this is always going to be final minus initial. And that becomes really important as we get into problems because the change in temperature can be negative, right? So we can have positive or negative changes in temperature, which is going to give us a sign of Q. And remember, the sign of Q is important because, as we discussed last time, it tells us whether heat is flowing in or out of the system. Yeah. So we want to make sure that we just don't take the change so it gives us a positive number. We want to make sure we're doing the final minus the initial, so we have to pay attention there. So this heat capacity idea is kind of a new concept. And so the heat capacity is really a property of the object or the material involved, and it is a measure of its sort of intrinsic ability to change temperature. So it really looks at how easy is it for the material to change temperature. So if an object changes temperature really easily, then it will have a low heat capacity, right? It doesn't take that much energy to change the temperature. If something has a high heat capacity, that means it takes a lot of energy in order for that material to change temperature. So what that means is that it's either going to have to gain or lose a small amount of energy if it has a low heat capacity, or gain or lose a large amount of energy if it has a high heat capacity in order for those temperature changes to occur. Now, the heat capacity of an object depends on a couple things. It depends on how much you have, so it's an extensive property, right? The more you have, the bigger the heat capacity is going to be. And it depends on, again, the type of material. So how much material we have, or so how much and what it is. Now, heat capacity is a useful concept, and we do use it, and we'll see an example a little later on in this section when we do what we call constant volume calorimetry. But heat capacity is really good when we have, say, a piece of equipment. That we use to measure these kinds of things. And it doesn't change, it's always the same mass. And so we can develop a capacity for that piece of equipment or that object. Now, a more useful idea or a more useful number for sort of general problems that we'll be dealing with is something called the specific heat capacity. So what this has essentially done is remove this idea of the amount, right? It's separated the amount of matter from the type of matter. And so the specific heat capacity is just related to the type of matter. And it's defined as the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So the amount of heat that has to either flow in or out of the material to change its temperature by 1 gram by 1 degree Celsius. And so just as I was talking about, right, this is really giving us the intrinsic ability of a material to absorb or release heat, right? How difficult it is. So the lower this number is, the easier it is for that material to change temperature. So if we look at a new equation here, where we've taken, again, our heat, but we've taken what was the heat capacity here, and we've divided it into two terms. One is the mass, so how much material we have now, and this specific heat capacity. Now notice the units here is joules, so energy per gram degree Celsius. So again, how much energy it takes to change 1 gram by 1 degree. So the energy per gram per degree Celsius. Okay. So we have to be careful with the units here because we need these units to be, correct in order to cancel everything out. And of course, the last part is the same change in temperature, right, that we talked about. So this is going to be, the equation that we use in most problems. Now over here, I've just given you a table of some heat capacities or specific heat capacities for you to reference. This is out of the book. This is not something you need to memorize, right? This is things that either going to be given in the problem or you can look in a table to figure out. But what I will point out is, certain types of materials that we know, right, like metals, for the most part, right, have relatively low heat capacities, right? And we know this, right? We know that metals heat up really easily, right? We use them to cook with, right, for this very reason, right? Because it's really easy for them to heat up. It's also relatively quick for them to cool down, right? So just a piece of metal, like just an empty pot, an empty pan, if you put it on the stove or in the oven, it's going to get hot really quick. But when you take it out of the oven, it gets cool pretty quickly. Whereas something like water, right, has a very high heat capacity, much, much higher than these metals. And you've experienced this, right? When you heat up water, it seems to take forever to heat up, right? Forever to boil, if you will, right? We heat it up. And it seems to take forever for it to cool down, right? This comes from the fact that water has such a high heat capacity. Okay, so now we have this idea of how to do it. So let's do an example. So our first example says how much energy must be absorbed in order to raise the temperature of 150 grams piece of copper from 25.0 Celsius to 75.0 Celsius. Okay, so if we think about our equation, right, we have Q equals mass times specific heat times delta T. So what do we know? Well, we have the mass here, right, 150 grams. We know what the material is, so we can find its specific heat. And we have the numbers necessary to give my delta T, right? So remember, delta T equals temperature final minus temperature initial. And so my final here is 75.0 minus 25.0. So my change is a positive 50.0 degrees Celsius. That's my delta T. So now I can look at my equation. My Q equals my mass, 150 grams. My material is copper, so if I go over to my table, I see the copper as value of 0.385 joules per gram degrees Celsius. And my delta T here is 50.0 degrees Celsius. If we think about units here, right, you'll see that grams cancel here and here. Degrees Celsius cancel here and here. So as we want our energy term, our heat here, right, is going to be in units of joules, as it should be, right? One of our units of heat. So if we do the math here, we get a value of Q equal to 2,887.5 joules. Now, significant figures, right? We're going to be at 3. So this is going to be down to 288. There's my 3. This rounds up, so 2890. Now, we could write this as 2890 joules, but we're better, of course, writing it as scientific notation to know that we have only 3 significant figures times 10 to the third joules. So, in order for this copper to be heated up by 50 degrees, it had to gain, right, notice the positive change here, had to gain, the system, the copper, had to gain 2,890 joules of energy. Okay, let's try a different one here. So here we have 12.5 grams of our material water, and the temperature changes from 101 to 25. So let's do my delta T here. So what is my final temperature? Right? That's 25, right? My initial is 101.0. So if I do 25.0 minus 101, I get a minus 76.0 degrees Celsius as my delta T. Okay, so it's okay to have a negative change, right? That just tells me the temperature is dropping. So if I go back to my equation, I have my Q, my mass, right, 12.5 grams. Now my material is water, so that means my specific heat is going to be 4.18 joules gram degrees Celsius. Temperature change. Again, my units cancel, degrees Celsius, grams. So I'm going to be left with joules. So if I do out my math, equals a minus 3,971 joules. Again, 3 significant figures is what's appropriate. So that would be 3970, but again, scientific notation is the better way to go. So our Q equals a negative 3.97 times 10 to the third joules. Again, indicating that in order for this water to cool down, it has to release, right? That's the negative sign, right? The system is losing, has to release 3,970 joules of energy in order for that temperature change to take place. Okay, one last example here, a little bit different. This one is a bit more involved. So here we have a piece of metal in a piece of water, and so we have a 32.5 gram piece of aluminum at 45.8 degrees Celsius. It's dropped into 105.3 grams of water at 15.4 degrees Celsius, and we want to know what the final temperature of the aluminum in the water. Now, one thing to remember is, right, these are going to be the same. So think about if we put a piece of hot metal into water, right? Eventually, what's going to happen is temperature will change or the heat will flow so that both of these things will reach the same temperature, right? So what we have to remember is the final temperature is going to be the same of the aluminum and the water. So that becomes important as we go through to solve the problem. Now, I said this one is a bit more advanced because we can't just do a simple Q equals MC delta T because we don't know all of these values, right? We're trying to find the T. We don't know the Q, right? We know the mass. We know the specific heats, but we don't know the Q. But what we do know is, if I think about this, that the Q of the metal must equal the negative Q of the water, right? So we can use this relationship so it looks like this. So the Q of the metal is going to be the mass of the metal, right? Or the 32.5 grams of aluminum times the specific heat of aluminum, right? So if you look at the table, that's 0.903 joules per gram degrees Celsius times the delta T of the aluminum. And this is going to equal the negative mass of the water, 105.3 grams, times the specific heat of the water times the delta T of the water. Okay, so we have this sort of basic setup here. So if we do some simplifying here, we can say 29.35 joules over degrees Celsius. So we do this multiplication, our grams cancel. Here and here, they'll cancel here and here. Times delta T of aluminum equals negative 440.15 joules degrees Celsius times delta T of the water. Okay. So I'm going to solve this so that we solve for the delta T of aluminum. So the delta T of aluminum equals negative 440.15 joules per gram times delta T of the water divided by 29.35 joules degrees Celsius. So if I do the division here, I get my delta T aluminum, which I'm going to rewrite here as temperature final of aluminum minus temperature initial of aluminum equals negative 14.997 times the delta T of water, right, which is, let's just T final water minus T initial water. Now remember that the T final aluminum equals T final water. So if I do plug in my T initials here, right? So I know for my aluminum, right, this is T final minus 45.8 degrees Celsius equals negative 14.997 times T final minus 15.4 degrees Celsius Now, I have to do a little math here, right? So we have to take the negative 14.997 and multiply it by both of these. So if I do this first, it's going to give me negative 14.997 TF. And then, so negative 14.997 TF plus, those negative signs cancel out, plus the 14.997 times 15.4 plus 230.95 . So now we can group terms a little bit here. And so we have a negative 14.99 TF. We have 1 TF over here. So if we add 14.997 to both sides, we get 15.997 TF equals, and if we add 45.8 to both sides, we get 276.75. And so we can solve for TF by doing the simple division now. So I'm going to move over here. So my TF equals 276.75 divided by 15.998 should get approximately 17.3 degrees Celsius as your final temperature. So while this is a little bit more complex problem, it's just showing you how these things sort of work together, right? And this is quantifying heat. So next we're going to move on to looking a little bit at work.